Hello, everybody, and welcome to episode 58 of the Hyperthesis podcast. I'm Liam.
I'm Patrick.
I'm Pheely.
All right, so today we've got the topic of our atmosphere and flows and related things regarding the atmosphere. I actually have no idea what we're going to talk about, honestly. It's on Patrick today. I did not read the notes, I'm sorry. But I did prepare an intro topic, so I'm at least 1/3 prepared for today. Yeah, so my intro topic is related to fluid mechanics, which is probably going to show up in Patrick's main topic a bit. Maybe, we'll see. But I found this interesting paper that was produced by a group of Chilean researchers who worked at various universities in Chile. And this paper was titled "Swirling Fluid Reduces the Bounce of Partially Filled Containers." So that's a pretty straightforward title. It was published on June 16th, 2023 in the journal Physical Review Letters. So imagine you have a solid plastic bottle, and I'm not talking about like those crinkly disposable plastic bottles you can buy in bulk at Walmart or whatever. I mean these reusable, clear, solid water bottles that last a very long time. If you have a Soda Stream, you can think of like a Soda Stream bottle. I don't have a Soda Stream, but I have a Soda Stream bottle, so that's the bottle that pops in my mind. And if you have this water bottle and there's no water in it and you drop it, it'll hit the ground and bounce back up in the air. A decent amount, actually. And that's because the bottle's empty and it acts as an elastic solid. So when it hits the ground, the bottle's deformed a very, very tiny amount, but it immediately goes back to its original form, so it bounces back up in the air fairly high. So it loses a little bit of energy, but not too much. However, if there's water in the water bottle, so say it's like half full, for example, it'll bounce typically much less higher in the air once it hits the ground after you drop it. And this is because when the bottle hits the ground, the impact causes the water to spread around and redistribute, and it dissipates energy from the impact into the water. So not all your energy goes back into bouncing the bottle back up in the air, and you lose a bunch of it in the water. So it bounces not as high as it would as if it were empty.
Would you call that a damped system because there's water in it?
Oh, geez. Yeah. It's damped in the sense that, yeah, it does. I mean, if it hit the ground and bounced up and down, if you have no energy loss, it goes forever. But in physics, if you have some friction or some energy loss, it eventually stops bouncing. So you call that a damp system, and it's damp because there's water. Just explaining it for anyone who might not get it.
A good way to think about it, if you can't really picture it, is bottle flipping. So when you have like these half-empty bottles that you flip and then try and get them to land upright, it's not bouncing at all. It's just kind of going splat and landing upright. And that's because it's half filled with water, which is what Liam's describing. Although, in that case, those tend to be the cheap plastic bottles, not these nice kind of solid bottles.
Yeah, I think what's helpful when I see those systems is that think of it, try to flip or throw the water up and keep it stable on the way down rather than the bottle, right? Because the majority of the mass of the system of the bottle is basically the bottle plus the water. And the bottle part is very little compared to the water. So if you try to throw the water up and down pretty stably, it should stabilize everything instead of trying to control the bottle, which is a small part of the system that's really susceptible to change.
Yeah, and I think not that this paper is about bottle flipping or anything, but I think the hard part about the whole bottle flipping thing, that's a really old trend. We're dated, but I think it's because fluids are a bit more complex and they do funny things that are hard to predict. They slosh around in funny ways, and so it makes it more difficult. Yeah, so coming back to this experiment, we're not flipping bottles, we're dropping them. And if you did it with one of these really cheap plastic bottles, like the reusable ones, it wouldn't bounce as high because those plastic bottles deform way more and you lose way more energy as they deform, opposed to like a hard plastic or a bottle made out of hard plastic. So no water, it bounces up fairly high. I mean, it depends on the water bottle and the surface of the ground and all that jazz. But when there's more water in it, it won't bounce as high. And it turns out as well that if the water in the bottle is rotating like a vortex, so think of like a whirlpool in the ocean, or think of a vortex around a bathtub drain. If you have that happening in your water bottle, so you hold your water bottle, you kind of rotate it around, you slosh it around so you get one of these whirlpools inside the water bottle and you drop it, it'll hit the ground and bounce even less. So it'll bounce way less than it would just having regular non-rotating water in it. So the kind of physics behind that is what this paper addressed. They wanted to kind of come up with a minimal model to describe why this happens. Why does spinning water in a bottle cause it to bounce even less than you might expect? And they did a kind of they did it experimentally, and then they kind of came up with a theoretical model to match their experimental results. So they found that the key to this effect it has to do with the key to this effect is the redistribution of the water during the impact of the bottle with the ground. And the water gets redistributed by the fact that it has angular momentum. So when I first thought of this, I was thinking like maybe it's the fact that there is angular momentum somehow causes this, but it's more so to do with the angular momentum causing a redistribution of water. So I have this water bottle. I shake it around so that I got a whirlpool in it spinning around. It has some vorticity, and I drop it. And as the water's falling, due to the vorticity, take a step back. Before I drop it, I'm just spinning the water bottle. The water's going around in a circle. It actually moves higher up on the edges of the bottle and kind of divots down in the middle, if you can picture that. I mean, I suggest go looking at this paper. They have really good pictures and things to match all the stuff I'm saying. But when you spin the bottle, think of a whirlpool in the ocean. The edges are higher in the whirlpool, and then they sink towards the middle. That's what's happening in your bottle. So as you let it go, it's still spinning as it falls. What ends up happening is because of this vorticity, the water actually becomes shallower in the middle than what it was before you dropped it. So you can kind of get this hollow tube of air in the bottle as it falls, and all the water kind of collects up around the edges of the bottle. It's still spinning as the bottle falls. The bottle then impacts the ground, and all this water on the edges of the bottle shoots down to the bottom, and it creates this spout that shoots up in the bottle in the middle of the bottle. So the water from the edges piles down and then shoots up the middle of the bottle. And I mean, if you have a plastic water bottle you don't care about, you can go see this. You can go test it yourself. And this is what causes the bottle to not bounce as much anymore, as if the water, compared to the case where the water is just motionless in the bottle. So the spout shoots up in the middle of the bottle, and it still has angular momentum. It's still spinning because of the original angular momentum. So centrifugal forces cause that water to now, in the middle of the bottle spout, to shoot outwards with a net kind of downwards, sideways force on the outer edges of the bottle. So you get a net force that's pushing down on the bottle. So it doesn't bounce as high because of that net force. So it's a lot to explain without pictures. So I really suggest go looking at the paper. They have really nice pictures to match that.
I'm just trying to think about any event in my memory that could have done that, right? Like we all drop pots or some buckets of water at some point, and I think all of us noticed that, well, it doesn't bounce. If maybe it's heavier, right? That's what people think. But you can see almost the same effect when you hit the ground. A lot of energy is pushed to the water and splurt the water up, right? When you drop a bucket of water, law of gravity dictates that everything falls at the same rate. And so everything should just hit the ground at the same time, bucket and water. But the water shoots up from the ground. But this is the case where You just add more spinning motion onto it. It has some vorticity, but the water still works the same because you know rotation and translation are kind of independent. That you can think of it separately and then combine it to form the full picture.
Yeah, it's one of these things where the bottle, when it hits if it's half full of water, it will do very different things when it hits the ground, depending on what the water's doing before you drop it. So the two simple cases I already talked about are if the water's doing nothing, the water bottle will fall, hit the ground, and it won't bounce quite as high as it did when it was empty. The other case is when it was rotating, like I just described. But you can imagine that it's doing all kinds of other things. You can slosh the water bottle around in some funny way and then let it go, and it'll be a bit more chaotic before, like once it hits the ground. So there's all different kinds of things you can do, but the mass of the system's the same in either case. It's just kind of like the initial state of the water causes it to bounce differently. And the two cases I've given you they're just kind of like simple ones. It's like not moving or it's spinning. So you can imagine there's more. And I don't know. I really like this kind of physics because it's very simple. It's like a really simple system. It's water in a bottle. However, and people have done this in the real world many times. I remember as a kid, I had one of these there's this science experiment you do in elementary school where you tape together two big empty bottles that are clear, and you can like siphon the water through them and spin it and create whirlpools as it transfers from bottle to bottle. This is all stuff we've done and seen before, but you can still think about the system a bit more carefully and say like, okay, when I do this specific thing, there's a reaction, and I don't really understand why this reaction occurs. And then you can sit down, you can make a simple experiment where you just spin water in a bottle and drop it, and you can create some new physics that people didn't know how to model before. In this paper as well, they actually give some applications of this in the real world. I don't really know anything about them, so it's in like the conclusions of the paper, so go read it. But it has to do a lot with like industry, I think, and also like transferring fuel in space and that kind of stuff, like production line things, I think, as well. So I'm sure there's some real world application that it'll have one day. It might maybe when they're transferring water bottles in some conveyor belt line and they drop the water bottles down, and like they'll spin them before they hit the ground so they don't bounce as high or something. I don't know.
Well, a lot of these systems are like this minimalist system, right? Like the smaller system can also give hints to how big a system work. What if, some kind of meteor hits the ocean, or some kind of, inhomogeneous meteor hit the ground, right? Like what if they somehow have liquid inside them that's somehow still liquid when it hits the ground? And what is the behavior of that meteor? And it's these kind of simple thought experiments are really useful in situating yourself and your mind, your head into this idea that nature is consistent across scale, or some kind of scale invariance in nature.
We love universality. Yeah, like I've talked about it once before, but I want to talk about it more in the future. Is when you microwave grapes, you create plasma, right? And there's a really famous paper on that and a really famous Veritasium video. But the researchers weren't microwaving grapes just because they could. They were doing it because the physics of the plasma in these grapes was transferable to microspheres, where you use these microspheres to kind of for signal generation, so you can like create. I like you think of a radio wave as a signal, right? You can use these for signal generation in physics experiments and real world and photonics, and so by understanding the plasma in these grapes, they better understood kind of this microsphere physics with ultraviolet radiation. So yeah, you can think of like, even though this is water in a bottle, maybe there's some application somewhere else that the physics transfers there.
Well, you say water in a bottle, but essentially what it is a fluid in a container, right? And it's like, well, what if how big is a container? Is the ocean a fluid with the container? Can you use the same thing to describe how the water and how the water behaved during the hurricane, right? Like what if that typhoon or not what's it called, the small one, tornado happens in a lake, a small lake, and what was the behavior of that water? It is interesting to think about it, isn't it? Like what if there's a big atmospheric event, or like a little tornado in this small lake, and are the waters gonna be all mushed up, a lot of vortices? Can we describe that, or should we describe that? And some people would ask, what would be the application? Well, the fishing industry might want to know if the fish gonna all die, or I think there are a lot of application you could think of,
that
when it
feels,
comes to studying nature.
I mean, that specific thing feels different than dropping the water bottle, but like the vorticity part, definitely similar. What was I about to say? I had a final point before we moved on to Patrick's main topic. Oh yeah, so if you, yeah, like you said, it doesn't have to be water in a bottle. It can be fluid in a container. It's just a water bottle is like a nice example because everyone knows what a water bottle is. If you put in something that's really viscous instead, so imagine you have this water bottle spinning. If you put in like some fluid that's more viscous, like maybe some kind of oil or thicker material, you might expect that it would bounce less, but it bounces higher because the viscosity causes less rotation, which causes less of this water to shoot out and spout out, and less of the water to kind of create this net downward force. So it's something counterintuitive, but because of this simple experiment and simple theoretical model they put to it, it makes perfect sense. So I don't know. I just really like these kind of I don't want to call them silly physics, but like I like these really nice little experiments and theories that people come up with.
So in this case, to limit the amount of bounce that happens, would you want a very dense, non-viscous, no, highly viscous fluid? I can't think of one right now, but I'm thinking like alcohol is more viscous than water, but it's less dense, right? So
it didn't. Yeah,
yeah.
I don't know if it had more so to do with the container the bottle's made out of. Because if your bottle is really stiff, then when it hits the ground, more energy is like transferred back into it, so it shoots back up. That's one thing, and the other thing is, I don't know about the I think I guess the density of the fluid inside. If it's more dense, then you're going to lose less energy when it hits the ground, I guess, right? So
Also, like, is it homogeneous, right? Is that are there air pockets inside? I think there are a lot of factors. Like a lot of physics we assume this homogeneity for everything. Like, everything is uniform. The rod in first year physics class, they're all uniform, and all the wood is uniform, has the same density of mass everywhere. But that's not true.
it's a good approximation though. Like water is an incompressible fluid, right? Like its density is pretty much constant. But other
Not when you have flow, yeah.
Yeah, exactly though, right? Like when you flow it around, then things change, and but yeah. So I guess
still
to say
believe the only thing we can describe well is not surprisingly well is the hydrogen atom. The rest is it's kind of murky.
Yeah, and even then, So Patrick, I think you want a dense fluid in the bottle,
but highly viscous.
Non-viscous. More viscosity means it bounces higher.
Right, yeah.
It's counterintuitive. The less viscous means that the water kind of, as it's spinning, it goes more towards the edge of the bottle, so the center becomes more hollow, which means when it hits the ground, that water in the edge shoots up the middle and then kind of like rains back down and causes a net downward force.
Right. So dense and non-viscous. Yeah. Got it.
Again, if you didn't follow this conversation, definitely open the paper up. I'll say it one more time before we move on.
We'll include it in the description of the episode.
Yeah, okay, we'll do that too. Swirling fluid reduces the bounce of partially filled containers in physical review letters. Um, Open it, listen to what we're saying, and look at their nice pictures. And that might be the best way to understand it, or just read what they have. So that was my little intro topic that I thought was kind of neat. But today we're here to talk about the atmosphere. So take it away, Patrick.
Yes, the atmosphere. It's all encompassing, very exciting. And I will preface this by saying I'm not an expert in atmospheric physics at all. If you are an atmospheric physicist, we would love to have you on as a guest, especially if your name is Simon Clark. That's just the only famous atmospheric physicist that I know that's still kind of recently off their PhD.
He had a child recently.
He did, yes.
I follow him on Instagram because he's friends with all the YouTube video gamers that I watch.
Yeah. So there's a lot of exciting things that happen in the atmosphere. So we're just going to touch on a couple of the basics here. And there are many forces, and there are two main things that lend themselves to what happens in the atmosphere that leads to this chaotic mess, which truly it is chaotic, that dictates our weather and conditions. Right now in Canada, we're starting to receive snow because there's less sun, so things are cooling down in the atmosphere. But it's still wet, so it's still producing snow. So there are a lot of things going on. Meanwhile, in Australia, they're getting into spring and the exact opposite of us. So to begin this main topic, I just want to talk about the basics of the atmosphere. Now, in a previous episode, we've discussed the different layers of the atmosphere as the final story. I forget which episode that was, but go and find it, listen to what the layers are, because these layers matter. There are defined boundaries within the atmosphere that really dictate what goes on within that layer of the atmosphere. So just as a brief reminder for if you aren't quite as familiar with the layers of the atmosphere, right against Earth, we have something known as the troposphere. So that's pretty much where almost all weather happens. There's an asterisk there, but all weather that we experience happens within the troposphere. That's where a lot of the clouds that we see, like the rain clouds, will form. Pretty much, again, a little asterisk there, but all of the clouds form within the troposphere, minus some very high altitude clouds. And we also interact with it the most. That's also the layer closest to the Earth, so it is the most dense layer. And then above that, we have the stratosphere, which is less dense. It's still has some weather events in there and weather events that affect us, especially here in Canada. Above that, we have the mesosphere. And then we have the thermosphere and the exosphere, which we really wouldn't be getting too much into. Kind of thermosphere, exosphere range is very, very low density atmosphere. I think the International Space Station is still technically orbiting within the atmosphere, but it's so not dense that it only needs to be boosted every once in a while to account for the drag effects caused by the atmosphere. But going down to the troposphere, which is and a bit of the stratosphere, which is what I want to focus on today, we get our weather. And especially in the troposphere, we have a leading cause of a lot of this weather, or at least something that influences greatly, and that is water vapor or moisture within the air. So if you've ever looked at the weather forecast for upcoming days, or even at the current weather, you'll see something known as humidity or relative humidity, and this is just the amount of moisture in the atmosphere versus what the atmosphere could hold before it just starts dropping out. So moisture plays a big factor in weather and the movement and components of our atmosphere, especially the troposphere.
I remember when I went home, usually we go during like the monsoon season, the humidity is around like 90 to 100% all the time, like 100%, right? We were like, oh, but we are not filled with water. But still it feels very like it feels like 100% humidity. Like it feels like if I put a water out, like a bucket water out, it evaporates somehow, that's gonna start the rain.
On the verge.
Yeah. No, and that's something with humidity is that if it's a higher humidity, it's actually dangerous to people because you sweat to cool yourself. The effort of evaporation or the energy that it takes to evaporate actually cools the body. If there's a lot of humidity, a lot of water in the air, you don't sweat as much. It can't actually evaporate into the air and you get hotter. You can't cool yourself. So if you're in a hot place, such as Thailand right now, just be careful, especially if you aren't from there. Pheely's fine. But
we would not be fine.
I mean, to be fair, Costa Rica, when I do field work there, it's like 40 degrees and 90+% humidity.
You might be okay then.
Your hair get a little poofy, right? Like when when it's very humid. Here, my hair is pretty flat, right? Like, and especially people with curly hair, it's really difficult to keep it down. It just puff up.
Yeah. So humidity not only plays a factor in your hairstyle, but plays a major factor in the weather of the troposphere. But even going back to more basics of the atmosphere, it's not just the shell around the Earth that's just sitting there doing nothing. It's moving. And what's causing it to move is uneven heating of the atmosphere. And in this case, that uneven heating comes from the sun. So the atmosphere itself is solar powered, you could say, because all of these circulations are caused by wind, which is produced by the sun. Now, just very basics of wind is you have hot air rising, cooler air moving in to replace it, and happening on very large scales over the size of continents. Then you get very interesting patterns. So not only windy days in a region, but consistent winds throughout an entire continent, for example. And we get things like the jet stream. But there's another effect that happens with large winds, especially ones that span continents, and that's the Coriolis effect. Now, the Coriolis effect is talked about in first year physics sometimes, but it's not always described very well. And it's essentially the fact that if you're on the equator, you're moving faster than someone, say, in Canada, because you're closer to the bulge of the sphere that is Earth. If you believe in the spherical Earth, which I would hope you would if you're listening to this podcast.
Please, I beg of you.
Well, one thing is that there's a little thing that because everywhere, let's say the Earth is a sphere. It's not a perfect sphere, but let's say it is a sphere. Any place on the sphere it has same radius from the center of the Earth. However, when it spins, it spins about a certain axis, right? There's an axis spin through, and now each point is not it's not the same anymore. Even though it's the same distance from the center, it's not the same distance from the axis. So the one at the equator is the furthest away from the axis. If you think of, let's say, a semicircle, right? So the distance from the middle chord, the chord in the middle of the circle, to the point on the curve is not the same. So that's why the Coriolis effect starts. But there's this misconception that's like the toilet in the southern and northern hemisphere, they go different way. Well, that's not the Coriolis effect, because this is the force of Coriolis is so minuscule to the water in the toilet bowl. But when it comes to hurricanes or big structures, because there's difference between the position of the top part and the bottom part and the middle part, actually, it creates this Coriolis effect, not the toilet bowl.
I think Veritasium maybe. I always talk about them. They might have did a video on this. I think in
Mythbuster? I'm not sure.
Yeah, I think in like a theoretically perfect world, the toilet bowls the way they spin, the water in them would be affect. I think the Coriolis force would dictate that in a perfect world, but it's such a
Yeah, but
small
I don't know.
effect.
I don't know if it will even overcome the tension of like the inertia of the water to even do
No,
that.
I don't think. Yeah, so it like realistically, it doesn't have an effect, but I think it's like if you ignore everything else, it would. But what you said for these bigger things like hurricanes and stuff, they see that more.
So just a note on that, it was, I believe, Veritasium and Destined from Smarter Every Day, and they actually filled up pools, one in Australia, one in the United States, and they actually showed that it does have an effect. But these are like 10-foot diameter pools.
Yeah, they created like a massive pool. They let it sit there completely still, and then they poked like a small pinhole in the bottom of it and just let it do its thing. And eventually, they rotate it like you expect based on the Coriolis force. But again, in the real world, like when you flush, a toilet, like there's so many other factors that come in that it's not going to matter where you are in the hemisphere.
But just for reference, so at 0 degrees or at the equator, if you are standing right on the equator, you're going at about just under 1,700 kilometers per hour. So that's how fast you're moving to make a full circle in about 24 hours at the equator. At 50 degrees, which is in Canada, just above our southern border, you're traveling only just over 1,000 kilometers per hour. So that's almost a 600 kilometer per hour difference between the two. Now, if you have a very strong wind that's moving, say, from the equator up north, so it's going, say, from 0 degrees up to 30 degrees, then once it reaches that 30-degree mark, it's going to be going a lot faster than the air around it. Because within those 30 degrees, it's dropped, in this case, about 300 kilometers per hour. So what you get from this is the start of circulation. So you have this faster moving wind that's moving sideways faster, essentially, than the air around it. And that's causing it to circle. Now, what's very interesting about this is that it actually will form patterns, and it will begin to form patterns across not just, say, a country or a continent, but around the entire Earth. And so these are large-scale patterns that happen within the atmosphere. And you may have heard of some of them, especially if you're in the northern hemisphere, such as the Polar Vortex or the jet stream, which is related to the Polar Vortex. So in this case, you have this easterly moving jet stream or stream of wind kind of higher up in the troposphere and also in the stratosphere that changes and moves as different atmospheric conditions change. But because of things like the Coriolis effect, it's going around the entire circumference of the Earth, around between about 40 to 60 degrees, depending on the time of year. And it will be stronger or weaker at different times of the year, depending on the temperature and other conditions of the atmosphere.
Is there a jet stream on the southern part of the Earth going the other direction? Is that a
Indeed.
thing?
Yeah.
Yeah, I was gonna say symmetry dictates there has to be, right?
Exactly, yeah. And of course, in the northern hemisphere, we have a lot larger land mass that's present than the southern hemisphere. But much like we have the polar vortex, there are polar vortices that form on either end of the Earth. However, they form at different times of the year, just because when it's winter in the northern hemisphere, it's summer in the southern hemisphere. So you'll have these kind of opposing seasonal vortices forming. And I think it's important to mention, talking about vortices, is the idea of cyclones. And no, these aren't the equivalent name of hurricane in whichever ocean, but cyclones are these large-scale circulations that happen within the atmosphere. So, for example, if you've ever heard the term bomb cyclone, where just a whole bunch of snow is released at the same time during the winter, and I know some news sources like to sensationalize it, like, oh, bomb cyclone coming for New York City. But this is just another type of large-scale circulation that happens. Now, another thing that's also a cyclone is, of course, a cyclone or hurricane, typhoon, however you call it, but this is just another type of large-scale circulation that results from the Coriolis effect. Now, hurricanes are a lot more dramatic because they not only have a lot of wind, they also have a lot of rain, and they make these incredibly cool shapes that you can see from space. And that kind of goes back to these vortices that Liam was talking about earlier, where you have these very relatively fast spinning cyclones that have a lot of moisture, which means there's a lot of clouds that has formed from the moisture, which are spinning quite quickly, bringing with them a lot of wind, and they're also moving.
Well, I remember around the year of like 2010 or like a few years before that, there was a big boom on the movies about the world ending from natural apocalypse, right? I don't know what happened to that trend, or maybe I'm just not following popular movies. But there were a lot of those like, oh, the big hurricanes, the tsunamis, the huge earthquake that happens, different scenarios. That I think when you are experience even any of those, even small scale, you start to realize that we are living in this very the world can be hostile not just by the living thing, it's by this inanimate thing. Just because we live on this volatile earth, there are volcanoes, there's stuff. I wonder what happened to those. Maybe it just fell off the trend. We now live in very peaceful, inter meteorological wise.
I think what happened is that people thought the world was going to end in 2012 for whatever reason. Something to do with a Mayan calendar. Don't quote me on
Oh, it's
that.
like a Nostradamus thing.
I have no idea, but I remember there was a movie called 2012 about the world ending. And leading up to that, there was a lot of movies about the world ending. And then, the world didn't end, so it just kind of stopped.
Yeah, I feel like we've progressed as a society, whether backwards or forwards. That's up to you to decide. But going back to these large scale events, with these circulations and these cyclones that happen, and these giant vortices that happen within the atmosphere, there are a couple very distinct patterns that pop up. And one of them is our circulation cells within the atmosphere. So going back to the equator, you have very direct sunlight. It's quite hot. You have a lot of hot air rising, and that hot air will rise, and cooler air from the north will rush in and take its place, which will then heat up. And what happens is you have these giant circulation cells within the atmosphere that will take that hot air, carry it kind of at the top of the troposphere, or maybe a little bit into the stratosphere, sink down at higher latitudes, and then rush back in to replace that hot air. Now, that equator circulation is what's known as a Hadley cell, whereas we also have mid-latitude cells and then our polar cell. And our polar cell in particular is what causes this polar vortex, because you have this Coriolis effect combined with this circulation going on, which forms this nice band of moving air in the atmosphere. And as the days get darker in the northern hemisphere, and of course the same is true for the southern hemisphere, it gets colder, and that polar vortex actually starts to tighten up and get more concentrated around the poles, which encloses the cold air within it. And this very cold air that's contained within it, if there's an instability within this polar vortex that causes it to shift or move, since it's containing that colder air, it will, if it's, say, stretched out, say, down over Canada, then that cold air will also move with it. Now, mind you, with all of this, there's things relating to high and low pressures. So, for example, for a cyclone, it has a very strong low pressure center. So, for example, with hurricanes that are in the Atlantic, it's very interesting to see because that low pressure almost acts like a straw that will suck up ocean water into a bulge centered around the hurricane. So if you're, say, on the coast and you can see there's a hurricane in the distance, maybe several tens or hundreds of kilometers away, it will look like an extremely low tide, and the water will be drawn away from the shoreline and into the where the hurricane is, which is a very interesting effect and one great example of atmospheric ocean interaction. But going back to things like the polar vortex, this is something that's sensationalized a lot in the winter as the polar vortex is becoming unstable and the polar vortex is causing temperatures to drop to minus 40 degrees. There's a lot of things that talk about the polar vortex, but don't really provide a good understanding. And it really is just the circulation that's happening around the 60-degree mark in latitude, in which it's able to trap this cold air, not only in the troposphere, where it's a bit more unstable and a bit more wavy, but also the stratosphere, where you have this kind of donut of circulation that holds in that cold air within the stratosphere as well. And what we're seeing is that as surface temperatures begin to rise, especially in the Arctic, we see that there's more instabilities with this vortex because you need that kind of nice gradient of temperatures as you go further and further south to maintain this vortex. And as you get variations or anomalies, it will destabilize the vortex and either cause it to split apart or just kind of destroy itself because, again, it's all a circulating mass of air and quite dry air too, since it's so cold, that will cause it to essentially become less stable and move further south. So even though things might be getting colder in winters, it will only last for a week or two as that polar vortex caused by warmer air in the Arctic destabilizes and moves cold air south. But there's a lot to cover in this, and we don't have a lot of time, but just a couple other things I want to mention, in particular, are large-scale oscillations within the atmosphere. So these are really neat and can take years to come to fruition, or in which we can see the results of the oscillation. But the most famous one is the El Nino Southern Oscillation, which is this incredibly powerful interaction between the ocean and the atmosphere that switches every couple of years. And depending on which way it is, whether it's what's known as an El Nino or a La Nina, will determine essentially what the weather is like globally for the year, which is pretty profound considering it's just a small effect within the southern Pacific Ocean having an effect on winters, say, in Canada. And I imagine a place like Thailand is also severely affected by the Enso cycle, as it's called. So this Enso cycle, or the El Nino Southern Oscillation, we're actually entering an El Nino year, but this has something to do with what's known as the Walker circulation. So instead of those latitudinally moving cells that we talked about before, the Walker circulation is caused by pressure gradient force that results from a high pressure system over the eastern Pacific Ocean and a lower pressure system over Indonesia. So what's happening there is that off the coast of South America, you have a high pressure, and off the coast of Indonesia, you have a low pressure. Of course, like everything else, things will move from high pressure to low pressure, and this creates this circulation. And now within the circulation, depending on how it's formed and which way it's going, it will either cause more heat to stay at the surface of the ocean, or it will cool the ocean. And this also has an effect on the ocean itself and the circulation, as the wind can actually drive this circulation. Now, there's a lot more to say about the Walker cycle. And I mean, again, if you're an atmospheric physicist or you work with the atmosphere, we would love to have you on. But essentially what happens is that in El Nino conditions, a warm water kind of section of this southern Pacific area will approach the South American coast, and the absence of cold upwelling from the deeper sea will cause an increase in warming. Now, in La Nina, warm water will actually be found further west than is usual, which will result in cooler water close to the coast of South America. And there's also neutral years where the pattern doesn't really change at all. It's as expected, where these equatorial winds will gather at the warm water pool and toward the west, and then cold water will upwell along the South American coast. But as we're entering an El Nino year, that means that there is more hot water present on the surface, which will cause more water to enter the atmosphere because it's evaporating since it's a bit warmer, which will then produce wetter conditions for Eastern Asia and large swaths of Asia. But then this will carry on over Africa and also over the equator, which is kind of a boundary, and it will cause different effects within the atmosphere. So, for example, in Western Canada, we are expecting to see I believe, slightly warmer winter than we would otherwise. And also with El Nino, as it's coming into full force, we expect to see hotter global temperatures. 2023 was already a record year for the highest global temperature on average throughout the year, and we expect 2024 to be even higher as El Nino causes higher surface temperatures. Now, there are other large-scale oscillations, such as in the North Atlantic, that we won't get into, and it looks like we're kind of running out of time. So I do just want to say a couple final things. One, the atmosphere is incredibly powerful. There are literal rivers filled with water within the atmosphere. It's very interesting. If you read about the Amazon, there is an aquifer under the ground that runs parallel with the Amazon. And then there's a river of moisture flowing along the Amazon as well. So the Amazon River itself is only part of it, with the atmosphere carrying quite a lot of moisture as well. And the other thing I want to leave you with is predicting the weather. We have these large-scale events, and we can see when, for example, the polar vortex is becoming unstabilized and predict where that's going to spread. You may have seen paths of hurricanes being predicted, and you kind of have this area of uncertainty. But predicting the weather is quite another challenge. I remember we were at a talk in our undergraduate once where someone who worked for, I believe it was Aviation Canada or something along those lines, but his whole job was predicting the weather and then relaying that to airports to know, like, okay, we need to divert these flights, or we need to delay or cancel these flights. He received a bit of flack from someone in that talk, but still, it's a very complex issue and something that's not perfect. How many times have you gone outside, it said there's no rain, and then it rains on you? So the atmosphere is very cool, very powerful. We only touched on it slightly, but please come talk to us about it if you are an expert in the atmosphere.
Yeah, if you can figure out a way to predict the weather, instant Nobel Prize, because chaotic systems are not great. But just because they're chaotic doesn't mean you can't do things with them. You can still model them and learn from it and make pretty good predictions. All right. Well, thank you very much, Patrick, for that. I love hearing about the atmosphere. The more into physics I get, the more interested I get in the atmosphere. So I have to talk to you about that later as well, because I need to learn more about it so that I can pursue my atmospheric optics hobby better. Next up, to wrap up this episode, before we have to hear a story from Pheely about Edmund Halley, who's famous for Halley's Comet. But before we do that, Patrick, you need to tell people how to reach us.
Well, there are many ways in which you can reach us, especially if you're an atmospheric physicist or atmospheric researcher. But really, if you are an expert in your field or have a very large knowledge about your field, we would love to have you on. And you can find us through different ways. The first being our email. You can send us an email. We are hyperthesispodcast@gmail.com. We check that pretty frequently. So if you have any questions, comments, or queries, feel free to send us an email. We can also be found on Instagram. We're at the Hyperthesis, and we post updates of when we are posting episodes. You may have seen the update for our last episode of when we'll be posting it. So keep an eye on that and give us a like and follow. And you can also DM us over the Instagram DM system. We are also on YouTube. up to the end of season 4 has been uploaded to YouTube, so you can check those out and share them. You can also leave comments, you can like, you can subscribe for updates. We're a bit slower with uploading our YouTube videos, but that's just because a lot of care and time goes into them. From Pheely, they have some beautiful graphics with them that are honestly mesmerizing. If you are listening to us, congratulations, you found us. And if you want to share us, we are on pretty much any podcasting service you can find, whether that be Google Podcast, which will soon be YouTube Music too, Apple Podcast, Audible. We're pretty much on whatever podcasting service you may use. So if you have questions, comments, queries, feel free to reach out to us and like, subscribe, do whatever you need to do, and share us as well. We are more than happy to spread our word to new audiences, and we also are interested in having you on if you are an expert in your field. So whether you're a grad student, a professor, retired, doesn't really matter. We are more than happy to have you on to talk about whatever area of science you specialize in.
Excellent. Thank you, Patrick. All right, Pheely, tell us about Mr. Halley.
Oh, I think it's Halley, but
Halley?
anyways.
I always hear Halley's comet. So
yeah, it's strange, but it has 2 L. But sometimes people say Haley, but I think it's Hall, Halley, right? It's Halley. Anyways, Edmund, or some people say Edmund even. Halley, Edmund, also can spell M-U-N-D too. So he was born on November 8th, so next week from the time of the recording, in Haggerston, Shoreditch, near London. And he actually died in Greenwich, near London. So he's an English astronomer, mathematician. So he was the first to calculate the orbit of a comet. That one, the one that named after him, the Halley's comet. And he's also noted for his role in the Isaac Newton's, I think the Principia Mathematica, which is the Newton's most famous work that he laid out the foundation of classical mechanics. But we will hear in the story how that came about. So Halley began his education at St. Paul's School in London, and he actually lived through this period of scientific revolution that comes about to become the modern science as we know it. So he was 4 years old when in the country the monarchy was restored with King Charles II. And they actually started the informal organization of philosophers called Invisible College. And then that Invisible College, quote unquote, is now known as the Royal Society of London, as we know it. So Halley entered Queen's College in Oxford in 1673 and was introduced to John Flamsteed, who was the Astronomer Royal in 1676. And so Halley visited the Royal Greenwich Observatory where Flamsteed did the work and really pushed him, right, or was encouraged to study astronomy. So with Flamsteed's project of using this telescope to catalog the northern stars, Halley wanted to do the same for southern hemisphere. It only makes sense, right? You do it for the northern hemisphere, you go to the south. And with the money or financial support from his father and from King Charles II, he went to the East India Company and sailed in November 1676 without finishing the degree from Oxford to the island of St. Helena in the Southern Territory in the South Atlantic that at the time the British has ruled there. And however, there's some bad weather that made the observations difficult. And then he actually went home in 1678. And he did record the celestial longitudes and latitudes of 341 stars and observed the transit of Mercury across the sun disk, and made some observations and noticed that some stars become fainter since their observation in the past. So, Halley's star catalog was published in 1678, and it was the first of the work to be published that have telescopically determined location of southern stars. So it actually helps solidify his reputation as an astronomer. And in 1678, he was elected as a fellow of the Royal Society. And he was granted the Master of Arts degree from the University of Oxford. And in 1684, around 6 years later, he actually visited Isaac Newton in Cambridge, of course, an event that really led into this huge development in the theory of gravitation. He was the youngest of a trio of Royal Society members in London that has Hooke, Christopher Wren, and Newton. So Robert Hooke, the guy who did the spring, the Hooke's law, and Robert Wren, the famous architect. So Newton, of course, we know who Newton is. And they were trying to find this explanation of planetary motion, how the planets move. And their problem was like, what force is keeping the planet in forward motion around the sun without flying off completely into space or falling into the sun? And now it seems so intuitive to us. Back then, they have not much clue of why things keep in this elliptical motion, or even circular or elliptical motion, or even concentric circle. So they're dependent on this scientific stature of the livelihood and sense of achievement, and they have their own self-interest of being the first to find a solution, right? You want to be the first to find it, get the reputation. And there's a lot of competition and rivalry between them. So Hooke and Halley reasoned that the force keeping the planet together in orbit must decrease as an inverse of the square of its distance from the sun. They weren't really able to deduce this hypothesis, an orbit that would match the observed planetary motion, even though there's a prize waiting for them if they really finished it. So Halley visited Newton, and Newton told him that, man, I already solved the problem. What are you talking about? The orbit would be an ellipse. But he had mislaid his calculations to prove it. I solved the problem. I just don't have the calculation that proved it, man. And I solved it. It's elliptical motion. Easy. And of course, people don't believe that. And so Newton then expanded his studies on this celestial mechanics into this masterpiece of a writing, the Principia Mathematica. And actually, Halley undertake the business of looking after it and printing at his own charge even. And he consulted with Newton and really smoothed out this dispute between Newton and Hooke, and actually helped edit the text of the Principia, and even wrote kind of a complement verse to honor the Newton, and corrected proofs and pushed it through the press and get it printed in 1687. So in all, Halley's has really huge effect on practical application of science in navigation, and really propel forward the idea of Newton. So even though Newton was definitely a genius, but he wasn't doing this alone. It's through this a lot of discussions, conversations, challenges, competition between other quote unquote scientists / philosophers at the time of how the planetary motion work. And the fact that Halley did all this work and then went to Newton and he solved it, which is quite skeptical. But his assessment of Newton's work and his persistence of finishing the work really put him into a very crucial place in Western civilization, coming out in this modern Western science and the scientific endeavor in general. So that is the story Edmund Halley.
Thank you for that, Pheely. I always thought it was really funny when he goes to Newton and Newton's like, "Oh, I did that a few years ago, but I can't find it. I've got too many piles of math around my study, so I'll just do it again." And then he, creates one of the most important texts of all time. And again, like, it was a collaboration, but I always thought that was kind of funny that he'd done it before, but he didn't really think to tell people about it. He was too busy doing other calculations and things. Anyway, thanks everybody for listening to our episode today, episode 58. That was a good one. Lots of vortices, lots of swirling things. We'll see you guys all next time. Bye.
Take care.
Bye, everyone.